solubility equilibria. So way back in Chapter 5 in Chem 1A, we learned how to use that table of solubility rules, right? And those rules allow us to calculate or classify different ionic compounds as either soluble or insoluble. But are there just those two extremes? No. It's actually a continuum, right? Some things are extremely soluble, some things are not very soluble at all, but like the quote said at the beginning of the chapter, there really is no such thing as an insoluble compound. Because if one formula unit dissolves, there's a solution, right? So we're going to look at degrees of solubility. The dissolution of a solid ionic compound is an equilibrium. So here we're looking at calcium fluoride. The solid, we put it in water, and it begins to dissociate into calcium ions and fluoride ions. But these can also run into each other again and reprecipitate back to the calcium fluoride. So it's an equilibrium. So we can use an equilibrium constant to describe this. We call that equilibrium constant the solubility product constant, or KSP. Solubility product. So we're looking at the concentrations of the products, right? This is a solid. It doesn't participate in K, right? So KSP for calcium fluoride would be the calcium ion concentration times the fluoride ion concentration squared, because we're getting twice as much fluoride as we have calcium. The larger the KSP, the further to the right the equilibrium lies, and the more soluble the compound is. So solubility describes how much of that compound dissolves in a certain amount of liquid. And if we talk about molar solubility, we're going to look at the solubility in units of moles per liter, so the molarity of the solution. We can we can calculate that from the KSP. It's important to note that KSP is not the molar solubility. KSP has one value at any given temperature. The molar solubility at that same temperature can be different depending on what else is in the solution, the common ion effect. So to find the molar solubility, we need to use an equilibrium calculation. So silver chloride, this is listed as insoluble in Chapter 5. Its solubility product constant is 1.77 times 10 to the minus 10. And that's a small equilibrium constant. So to calculate the molar solubility, we look at this dissolving, and it forms one silver ion and one chloride ion. And so ice table. Initially, we have 0 and 0. As 1 mole of this dissolves per liter, I'm going to get 1 mole per liter of silver ion and 1 mole per liter of chloride ion, right? So that's S, the molar solubility, moles per liter. So at equilibrium, the concentrations there are both S. So, KSP for this one is equal to the silver ion concentration times the chloride ion concentration. This is equal to S, and that is equal to S. So it's equal to S times S. Trying to make sure those don't look like 5s. So KSP equals S squared. So if we want the molar solubility, S is going to be equal to the square root of KSP. So we'll have 1.33 times 10 to the minus 5 moles will dissolve in a liter of solution. That's not very much. That's a low concentration, right? Any questions? We cover this a little bit in Chem 3A. And, oh my goodness. That's hard for them. It's really hard. You're in a much better place to understand it. So here's a table from your book, selected solubility product constants at 25 degrees Celsius. So you can look up these different compounds and find out what their solubility product constant is. So if you have a homework question where they don't tell you what KSP is, you need to go look it up. There's also a table in the appendix at the back with a lot more KSPs. So if it's not in this table, it might be in that table. Calculate the molar solubility of iron hydroxide in pure water. KSP is 4.87 times 10 to the minus 17. Well, first we need to write the equation for this compound dissolving, because we need to have the equilibrium expression for KSP. So we have iron hydroxide, solid, in equilibrium with, what are the ions that it forms? Yeah, we've got iron 2 plus, that's aqueous, and 2 hydroxide ions. So if we make our ice table, we're starting out with 0 for the initial concentrations. This one is going to change. When 1 mole of this dissolves, we get 1 mole of this, right? So that's going to change by plus S. What's this one going to change by? Plus 2S, right? So at equilibrium, this is S, and this is 2S. KSP equals Fe2 plus concentration times the hydroxide ion concentration squared, right? We didn't run into a lot of that when we were talking about acids because most of them are monoprotic. So KSP is equal to S times 2S, the quantity squared, which is equal to what? 4S cubed. So KSP equals 4S cubed. So how do we solve for S? So first we're going to divide by 4. Get rid of that. Then we're going to take the cube root of the whole thing to get rid of that. So the TI-36X Pro has a button that looks like this. It's a second function. it's the second function of the x to the square button. And so what you do there is whatever root you want, you type that in. So I'm going to go 3, and I'm going to do that button, and I'm going to do 4.87 times 10 to the minus 17 divided by 4, and press equals. Times 10 to the minus 6 molar. What if you don't have a button like that? Raise it to the 1/3 power. The square root is something raised to the 1/2 power. The 5th root would be raised to the 1/5 power. So you can prove that to yourself if you like. I take the KSP and divide by 4, and then I'm going to take that and raise it to the 1 divided by 3, and I get the same answer. It's best to use a fraction there instead of 0.33, because it's actually 0.33 repeating forever, right? And so if you can avoid rounding, it's better. Any questions? Yes.
So let's just imagine that we have an exothermic chemical reaction.
Mm-hmm.
If we add heat to the equation, to the reaction, then it shifts to the left.
Yes.
And K reduces, right? The value of K reduces.
Well, the value of the equilibrium constant is somewhat dependent on temperature. But if you're just thinking about the effect of that heat, it's not shifting because K is changing. It's shifting because heat is a product, and you put more heat in there, and Le Chatelier's principle tells us it'll shift towards the reactants. But it's a bit complicated because the Ks are different.
Right. But what happens if it then later on it comes back to normal, to the standard temperature? Will it shift back right to the right?
Yes, I think it will.
Okay.
Yep. Yeah.
Is the KSP something like salt, sodium chloride, infinite?
It's not infinite, no. Let's see if it's on the table. It's not. These guys are all pretty insoluble. If the KSP for sodium chloride was infinite, then you could dissolve an infinite amount of infinite moles of sodium chloride in water, and you can't. You can dissolve an awful lot, but there's a limit. Yeah. So we're turning it around here. Calculate the KSP given the molar solubility. Well, we're going to approach it in the same way. Let's look at what's happening here. Silver bromide, solid, in equilibrium with silver ions and bromide ions. And I think you probably realized that if you didn't get nomenclature and ionic compound stuff in Chem 1A, you're going to be hurting, right? Because we need to be able to just write equations like this without too much difficulty. So if we think about an ice table and solubility, starting with 0 of each, how is the silver changing with regard to the molar solubility?
Yes.
It's going up by plus S. And bromide is also going by plus S. So the change here, we're going to use S instead of X. S is the molar solubility. If there's a number in front of it, it's because there's a coefficient in front of it. So if this was 2Br, it'd be 2S. So this is S and S, and we see that the KSP is equal to S squared. because it's this concentration times that concentration. Well, here's the molar solubility. So we can just plug that in here. And square it. Five 5.3 times 10 to the minus 13. Okay? This is really just a variation on what we've been doing. So the molar solubility and KSP are related to each other, but you can't just compare KSPs to get relative solubilities. And the reason is that the relationship depends on the stoichiometry, right? If it's one of each ion, KSP is the solubility squared. If it's one ion and two of another, then it's 4s cubed, right? And that's just very different. So here, what are we looking at? Here we have magnesium hydroxide and iron carbonate. Well, iron carbonate has a 1-to-1, one ion of each kind, and this is 1-to-2, right? So here the KSP is smaller, but the solubility is larger because of the stoichiometry. Down here, if we're comparing two that have the same stoichiometry, two anions to one cation, and we look at the KSPs, magnesium hydroxide has the smaller KSP and the smaller solubility. So you can only compare if the stoichiometry is the same. So we talked about the common ion effect when we talked about Le Chatelier's principle. In general, the solubility of an ionic compound will be lower in a solution containing a common ion than in pure water. So here we're dissolving calcium fluoride, and if the initial concentration here was 0, then we can predict what's going to happen by looking at the KSP. If we add common ion to this, if we add fluoride, how does that affect the equilibrium? Well, it shifts it to the left, right? You add product, it shifts towards the reactants. So if you're dissolving this in a solution where there is already fluoride, it's just not going to go as far, and the solubility is less. So let's calculate that. Calculate the molar solubility of calcium fluoride in a solution containing 0.250 molar calcium nitrate. So we'll write the equation for calcium fluoride dissolving. We get calcium ion and 2 fluoride ions, right? Now, when we make our ice table, what's the initial concentration of calcium ion? It's 0.250. And you have to be a little bit careful, because if we were looking at nitrate, there's 2 of them, and it'd be twice that, right? But we're looking at the calcium. So the initial concentration is 0.250, and the initial concentration of the fluoride is 0. So how is this going to change in terms of S? It's going to increase by 1s. and the fluoride by 2s, right? So now we've got 0.250 plus s, and we have 2s. KSP is the calcium times the fluoride squared. So that's 0.250 plus s times 2s squared. That is equal to 1.46 times 10 to the minus 10.
Why is it squared again?
It is squared because there's a 2 here,
It doesn't matter that it's already considered, like with the 2s.
but the 2 gets squared too.
Oh.
Yeah. Because for every one of these, I get 2 of these. And the equilibrium constant thing says I raise it to the power of its coefficient. And if you think about it a little bit, but not too hard, it's kind of crazy that it actually comes out to be this simple, right? It's just a concentration raised to the power. And that describes equilibrium. That's like, a little suspicious. It works. So how would we solve for S? We could use the solver. Yeah. You can always use the solver.
Yeah.
Solver's awesome, right? What if we didn't have a solver?
Also, it is,
We could try S is small, right? So somebody do it on the solver, and I'm going to do S is small. What'd the solver give you? The same?
1.21 times.
1.21. And this is 1.208. The reason that approximation works is because adding this small number onto 0.25 really doesn't have any effect. It's like taking the mass, the weight of a semi-truck full of oranges, and you toss one more orange on top. Does it matter? No. It's so small compared to what is being added to. But just remember, you can't always do S is small. In which solution is barium sulfate most soluble? A solution that's 0.1 molar in barium nitrate, 0.1 molar in sodium sulfate, or 0.1 molar in sodium nitrate? C. It'll be more soluble there because it doesn't have any common ions. Both of the previous ones have common ions. pH affects solubility because pH affects the concentrations of some of the ions. So here, looking at magnesium hydroxide, Magnesium hydroxide dissolves to form magnesium ion and 2 hydroxide ions. So if we are in a solution that's basic, that has a lot of hydroxide ions, that's a common ion, right? And so that's going to push the equilibrium to the left and make the magnesium hydroxide less soluble. If we're in an acidic solution where there's hydrogen ions, they're going to react with hydroxide, removing product, and cause the equilibrium to shift to the right. I don't know if you remember, but in 1A, like when we did the oxalic acid titration, you want all of your acid to dissolve right away, but sometimes it doesn't. And the procedure says, if it doesn't dissolve right away, don't worry about it. Just make sure it all dissolves when you get to the end point. Well, this is what makes it dissolve. It's just going to dissolve much easier as you pull away ions. So generally, the solubility of an ionic compound with a strongly basic or weakly basic anion increases with increasing acidity. So some common basic ions are hydroxide and sulfide and carbonate. We talked about acid rain. Rain is naturally a little bit acidic just because of the dissolved carbon dioxide. So as rainwater flows through limestone, it can partially dissolve, it can start to dissolve it. And the result can be these huge underground caverns where rainwater over a long, long period of time has dissolved the limestone and it's run away. Limestone is calcium carbonate. And so as this water that's dissolving the calcium carbonate drips and evaporates, it will leave calcium carbonate deposits behind. And that can happen at the bottom of a stalactite or at the top of a stalagmite. You know how you remember the difference between those two?
Stalactite has C, ceiling.
Well, that's good. Stalactite has C like ceiling. Well, I think of it as these kind of look like tights hanging from the ceiling, and this is a mite, a little guy, right? Stalagmite. That's how I remember everything, is I find something like that. Which compound, iron carbonate or lead 3 bromide, is more soluble in acid than in base? Solubility of an ionic compound with a strongly basic or weakly basic anion increases with increasing acidity. So here we're talking about being more soluble in an acid. Iron carbonate. Oops. So iron carbonate, the carbonate ion, is a base. Right? So this base acts with or reacts with the hydrogen ion in the acidic solution, removing the product and causing the reaction to go towards the products, increasing the solubility. Any questions? Can I repeat that? I'll repeat it with visuals. Oops. So, iron carbonate dissolving, right? It forms iron ions and carbonate ions. If I have a lot of hydrogen ion present, a lot of acid, this is a weak base. It's going to react with it, right? It's going to react with it to form hydrogen carbonate ion or maybe even carbonic acid. But the result is the same. I'm removing product. The acid is removing product. So Le Chatelier's principle says you take away product, equilibrium shifts to the right.
Oh,
Okay? Once you see it, you're just like, oh, yeah, yes.
Shouldn't we have to worry about high charge cations forming water complexes from the last chapter, like in the lead ions?
That's a good question.
Or is that not considered?
So this is Fe2 plus, and the one that acted as an acid was Fe3 plus.
Oh, I mean for the lead.
For the lead is not small. Yeah. So lead is way down here. Lead's a big guy. Yeah. But a good question.
So it's too big to form a water.
Yeah, it's not going to act. It's the small, highly charged. So like, cobalt and iron, those guys are small. Yeah, they're up there in the third period? Yeah. Whereas lead is down in the sixth period. And as you go down, things get bigger.